Today we will learn what are the types of finite state machines available. Since we are now studying this finite automaton, so we have learned DFA, NFA and so far their conversion, how to minimize DFA and all that. Now we will see the machines where this finite automaton can be processed and how to design those machines, what are the theory underlying those and so on. Okay. So first, finite automata may have outputs corresponding to each transition, right? So in case of finite automata, what we have done in NFA DFA, we have just seen that for a particular input, right, for a particular input one state is transiting to another state, but we have not considered while transiting from one state to another whether they are generating any outputs or not. Fine, we only focused on the state and the input value, no outputs were there, but now this machine we will focus on the output part as well. There may in if we move on to compiler design and all other things, obviously the thing may be like this, that during for a particular input, for processing that input, ultimately it may generate some, it may come out with some output. In that case, that NFA and DFA will not work. So here we learn about two machines. One is called Mealy machine, another is called Moore machine. First we will learn what Mealy machine is. Right, here if you remember, the NFA and DFA were 5 tuple machines, but here what we are doing, we are incorporating one more tuple named output set. Fine, rest will be same. So 6 tuple, what are those? One is Q, obviously the set of states. Sigma is a set of inputs. O is a newly introduced one, that is set of output states. Delta is our transition function, and another thing, X is the obviously what new thing we have to do. This delta will focus on the transition of input, means for a particular input what it is doing. Combination of one state and one input symbol will generate one new state that delta looks after, right? Here X will do what? For a particular input at one state, what output it is generating. It is not focusing on which state it is moving, it is focusing only on what output it is generating. Now it will another thing here, no final state is so far mentioned, so Q0 will be initial state. So here our job will be not only to find out whether this string is acceptable or this string is reaching to final state or not. We will design in a fashion that when some input is applied to a particular state, what output it is generating and to which state it is moving, that's all, right? Okay, now see the transition table, how to do it. In case of Mealy machine, just focus on Mealy machine, we will see the difference in Moore machine. It will act in some different fashion. Here what it will do, it will, whatever output it will generate, that output will depend on both the input value and to which state it is transiting, right? I am repeating, in this case what output one transition is generating, it will depend on both to which state it is moving and which input value it has been fed. Fine. So as the table suggests, here A is our initial state, both two inputs are there, one is 0, another is 1. So what we have to keep in mind, for 0 at A, to which state it is moving and what output it is generating. So if you develop this 6 tuple, so Q will cover A, B, C, D. Input set, that is sigma, will cover 0, 1. Output set, it will cover x1, x2, x3, right? Then your transition function delta will cover, say, A comma 0 will generate B. Then another transition function x will generate what? A comma 0 will give our x1, right? So first delta will do for a particular input at one state to which state it is transiting, and what x will do for a particular input at one state, what output it is generating. Fine. Next, obviously Q0 will be the initial state, that's all. Okay, now let us draw the transition diagram corresponding to this. Here you will be able to see that for a particular transition, for which input value it is moving to which state and what output value it is generating. You can easily understand that here input slash output, this pattern has been followed, right? So if you focus on A, if we give 0 to A, it will move to B, and at the same time it will generate the output x1. In this fashion, for 1 at A, it will move to C and will generate the output x1. Similarly for B, C and D. You can consult the diagram you can consult the table and can draw this transition diagram. Okay, next we will see what Moore machine is. The same thing, 6 tuple machine, everything is okay, everything is similar to Mealy machine. Only if you see the output transition function, what it is doing, it is not depending on the input value, it is simply depending on to which state we are moving to. Whatever may be the input value is, if we have moved to one state, we will not keep in mind what was the input value. We will just see to which state it has moved and we will generate the output there. So here output generation is depending on to which state we have transited to, not the input value. But in case of Mealy machine, we have seen to which state we are coming to and for which input value this transition is possible. Both the condition were required to generate one output. Fine, rest are same. So now let us see the table. So since it is not depending on to the means it is not changing with the input values, so we will just separate this next state into two categories, that is for input 0 and input 1. We are not finding out for which the pair of input and the next state. Okay, so if you consult the diagram for A, whether when the input is 0 it is generating B and when the input is 1 it is generating C, but the output will be fixed since it is not depending on the next state. Fine, it is fixed that A will always generate the output x2 wherever the transition is. Similarly for B, you can see it is moving to B for 0 input, for moving to D for 1 input, and B is generating the output x1. So in this fashion C and D, you can consult the diagram and can make this table. Okay, not diagram, sorry, this is the table initially given, so this they are following this one. So using this table now we will draw the diagram. So just see what we did there. We were making the pair of input slash output in the Mealy machine, but in Moore machine, since it is not depending on input at all, we will associate the output with that state only. So if you consult the table, you will be able to see that A's output is always x2, B's output is always x1, C's output is always x2 and D's output is always x3. Now just make the transition for 0 input value where A is moving, for 1 input value where A is moving, for 0 input value where B is moving, for 1 where it is moving, and similarly for C and D. Right, I think this is very easy to understand. Now I have make a table for your simplicity. You may just follow the steps. I have already explained how Mealy machine and Moore machine differs. I am not explaining again here. Just follow the steps. If you fail to understand, then obviously in doubt clearing class we will clear all those. Okay, next our job will be to convert from one machine to another. First we will convert Moore machine to Mealy machine. So what the changes we have to do? In case of Moore machine, again I am repeating, each output is depending on the state, but in case of Mealy machine it is depending on both, to which state it is moving and what input value it was fed. So you can follow the steps, but I will directly move to the example so that it will be easy to understand. Okay, so this is the Moore machine given. See, here the inputs are 0 1, again outputs are 0 1, and states are ABCD, where A is the initial state. Since this is Moore machine, so what the output will be, it will depend on the state. For A output is 1, for B output is 0, C it is 0, D it is 1. But if we have to convert to Mealy machine, what we have to separate? we have to separate the outputs for both a equals to 0 and a equals to 1. Firstly, what we will do, we will just separate these two, for a equals to 0, for a equals to 1, right? And we will just mark the states where it is moving, and we'll keep the output column blank for now. So for a equals to 0, a is moving to d. For a equals to 1, a is moving to b. Similarly for b, it is moving to a and d respectively, and so on. Now, how to write this output? If you consult the previous table, what a is generating, a is always generating output 1. So let us focus on where the next state is a. If you find out for present state b, for value a equals to 0, our next state is a. So in the output column, we will write 1, right? Now here d is always generating the output. I am focusing on present state. Do not get confused with the next state. D is always generating output 1 in case of Moore machine. So here we will see where the next state is d. If you see the table, for a equals to 0 means for input 0, a is moving to state d. So the output will be 1. In this fashion you can complete the rest. Fine. Okay. Next, we will do the reverse process. If we are given one Mealy machine, how to generate the Moore machine. Again, I am not explaining the steps. You can just read it out. We will move to example directly. Fine. So this is our Mealy machine given, where there are 4 states A, B, C, D. A is initial state. Both of them are separated into 2 parts. One a equals to 0, another a equals to 1, and each output is associated with both input and next state. So what we have to do here, we have to only keep only one output corresponding to each state. So firstly, what we will do, we will just write means the present state, and for a equals to 0 what it is doing, for a equals to 1 what it is doing, and leave the output for now. I am explaining later on. So for a equals to 0, a is moving to d. For b equals to 0, it is moving to a, right? For b, and then b equals to 1, it is moving to d. Why b1, c0, c1, I will explain later on, right? Okay, first just write this much. Now what the output of a will be, if you consult the table, you can see that at a equals to 0, for present state b, the next state is a, and the output generated is 1, right? Again, for present state d, for input a equals to 1, it is moving to a state, and the output generated is 1. Here the generation of output is same, right? For both, when b is transiting to state a for input 0, it is generating 1. For present state d, when it is moving to the next state a, again it is generating the output 1. Means what we are doing, we are doing nothing. We will just focus on the next state and find out where a are lying, and we will see the corresponding outputs. If it matches, fine. In case of a, it is matching, that's why we have written the output as 1. But if you see in case of b, if you see the previous table or Mealy machine table, you can see it at one place, means where present state was d and next state was b, it was generating the output 0. But when our present state was a and next state was b, it was generating output 1. That's why we have separated b into 2 halves. One is 0, another is 1. See here, next state means a, for transition means the next state for equals to 0 and equals to 1, that both of them will move to a and d respectively, but the output is different, right? Similarly the case of c will be, but in case of d, again if you see the next state and output pair, in both the places d is generating the output 0, right? So just put your focus, a little bit focus in it. and it will be clear to you. Okay, fine. So this is the end of today's class. Next day we will learn regular expressions. Regular expression is a very important part, so that we can move to regular languages. And regular language is nothing but a language in which our finite machine or finite automata or DFA, NFA, your Moore machine, Mealy machine will generate. Thank you.